Hello, everybody. What I'm going to be doing now is a section on 8.3, which is moments and centers of mass. So we actually already did an application, so this is application 2. So if you recall, application 1 was hydrostatic force, so this is application 2. So let's talk a little bit about this. You've probably heard of the word center of mass before. Every object has what we call a center of mass. And the way we define this is a point where we can consider all of its mass to lie. For example, in a physics class, when we treat an object like it's flying through the air or something like that, we don't actually treat it like it's a giant object. We actually treat it like it's a point. So that's what we're trying to figure out now, is where is this point actually located if you know where this entire object is. We also refer to this point as a centroid. I will use the word centroid a lot because it is a nice compact way to do this. Or center of gravity. I don't use this one very much, but it's good to know different words for the same thing. Okay, so in one dimension, this means you can picture, for example, a rod. Then we have some center of mass, which we can call, we can call that x bar. And in 2 dimensions, this means we have, so if we want to call this guy a rod, we have something called a lamina, which is a 2-dimensional shape. This is a lamina. Okay? Let me write that a little better there. And in 2 dimensions, we start to talk about something called density, right? Because some objects are more dense in certain places than others. So, one more thing too, the density is going to be somewhere in there. And maybe it'll be in there, but this is given as x bar, y bar. Now, in 2 dimensions also, we start to talk about the density. So, we refer to rho of x, y as the density of the object. So in this class, so in single variable calculus, so in math 70, rho will always be constant. In math 80, which is multivariable calculus, rho of x, y will be a function. Now the reason we cannot do these in this class is because to solve this, you need a double integral. So we're not going to be doing that in this class. Okay? So finally, we go with the 3-dimensional case. So in 3 dimensions, we have, we have some shape. And maybe it's inside there somewhere, and this would be X bar, Y bar, Z bar, right? This is a solid. And we deal with this specifically in Math 80 only. You're going to learn how to do that in that class. Okay? So let us begin with 1 dimension. We begin our discussion with something called a moment. So the moment of a particle located at x1 with mass m1 is going to equal its mass times its position. Okay, so this is just, think of this as a weighted, you're giving the location of the object, but you're also multiplying it by its mass. Okay, so it's like a weighted mass or weighted location. Now, this isn't very useful because it's only one particle, and of course, if there's only one point somewhere, the center of mass is just going to be that point, okay, wherever it's located. So this only becomes useful when we have many particles. So let's talk about what happens when you have n particles. The moment of a system containing n particles let me go with located. So located at x1 all the way up to xn with masses m1 to mn respectively, so when you have a bunch of these guys, all you have to do is add them all together. So the moment of a system containing n particles located at x1 to xn with masses m1 to mn respectively is the sum of all their moments. Okay, so what this means is that the moment is going to be the sum of all of these products, mi, xi. Okay, so for the next part, we're going to let m be the sum or the total of all the mass. So let's let this be the total mass of the system. Then the center of mass simply becomes capital M divided by M, which is the same as MIXI divided by MI. Okay? So this is very, very basic. All we're doing is saying a weighted, this is how you find the location of the center of mass, is you just add up all of the moments of the n particles and then divide it by the total mass of the n particles. Where have you seen this idea before? You've actually seen this idea before when you find your GPA. So how does that work? Well, if you think about it, the mass of each grade, when you get a grade, it's given by the number of units, right? Think about the weight that something has on your GPA. For example, if you get an A in a 5-unit class, that affects your GPA more than a weight in a 3-unit class. You can think of the 5-unit class, the A in there having a heavier mass, right? Because it's 5 whole units. So you multiply the number of grade points by the number of units for each grade, and you add them all together, and then you divide it by the total number of units. This is exactly how GPA is found, and it's the exact same idea. Okay, so let's move on to 2 dimensions, and we're not going to see any examples in 1 dimensions. We still haven't done any calculus, by the way, and you guys will see when this comes up. So for the next part, we're going to talk about 2 dimensions. So now what we have is we have n particles. Except now they are located at x1, y1, x2, y2, and the last one is going to be at xn, yn, with masses m1 to mn respectively. So the trick here, when you have n things all scattered around, is you actually realize that all n of these points are weighted with a mass with respect to the x and y axis in the same way. Okay, so what am I saying? I'm saying that we actually need 2 moments now, 1 moment with respect to the x-axis and 1 moment with respect to the y-axis. So let's write this down. mx will be the moment with respect to the x-axis. And what would this formula be? So we need to think, how far away is a point from the x-axis? So if you have a point, maybe I will draw this point here. And so let's say it's sitting right there. And let's say the coordinates of this point are x, I, y, I. And this is xi, therefore, and this is yi, right? So how far away is this point from the x-axis? Well, it would be this distance right here, which is actually yi, isn't it? Therefore, the way you calculate the moment with respect to the x-axis is you actually add up all of the masses times the y-coordinates of the point. Okay? And again, the reason is because the y-coordinate of a point tells you how far away from the x-axis you are. Second, my, of course, as you can expect, this is the moment with respect to the y-axis, which is going to equal this. Okay? Again, same idea. It's because this dot is a distance of xi away. Finally, how do we find the centroid? So the centroid, center of mass, we are looking for x bar, y bar. Well, you just find x bar and y bar with the formulas we had before. So x bar is going to equal the moment with respect to the y-axis divided by m, and y bar is equal to the moment with respect to the x-axis divided by m. Now I know that seems weird and backwards that we have an x bar but then a y in the actual formula, but that's because of the flip. If you actually were to write these out, it makes sense because these are actually all of the x coordinates involved. There are no y coordinates at all involved in x bar. And then over here, same idea too, right? We have mi yi divided by mi. So this is how we find x bar, and this is how we find y bar. Before I move on, I'm actually going to do an example. So this is going to be our number 1. Find the moments and center of mass of the system of objects that have masses 2, 5, and 11 respectively. Oh, sorry, that word shouldn't be there. Have masses 2, 5, and 11 at the points -1, 1, 2, -1, and 3, 2, respectively. Okay? All right, so let's go ahead and figure this out. We're going to start with doing the moment with respect to the x-axis. So this is going to be, if you recall, the sum of all the masses times the y values divided by the sum of the masses. So what's this going to equal? Well, we've got 2 times, so this guy has mass 2, this guy has mass 5, and this guy has mass 11. So it's going to be 2 times 1 plus 5 times -1 plus 11 times 2. And oh, sorry guys, I made a mistake here. What we're looking for here is just the moment, not the center of mass, so I didn't mean to put divided by, okay? So we have 2 times 1 plus 5 times -1 plus 11 times 2. We end up with 2 minus 5 is -3. -3 plus 22 is 19. Okay, 19. Okay, Next, we have the moment with respect to the y-axis, which means we actually sum together the products mi times xi. And same idea, except we now use the x-coordinate. So it's going to be 2 times -1 plus 5 times 2 plus 11 times 3. So this is -2 plus 10 is 8 plus 33 is 41. So these are the moments, and the problem did ask us for the moments and the center of mass, so this is one of our answers. This is our other answer. Now we need the two centers of mass. Let's go ahead and figure out what m is, because we are going to need this in a second. So the sum of all the masses is going to be 2 plus 5 plus 11, which is 18. And then finally, we're ready for the center of mass. X bar, remember, is going to equal my divided by m, which in this case is 41 divided by 18. That does not simplify. And y bar is equal to mx divided by m, which is 19 over 18. Okay, so this means that the centroid is equal to the point 41 over 18 comma 19 over 18. Okay. Now, you may be wondering, where does the calculus come in, right? We have not used any calculus so far. So what we're going to do now is the case where we have a lamina. Okay, of course, the lamina is going to involve constant density, because otherwise we would need double integrals to do this problem. Okay, so let's talk about a lamina. A lamina, in normal cases, is just a two-dimensional region, except ours is going to be very specific. Ours is going to be a function y equals f of x, where x is going to go from a to b, and r is going to be a lamina bounded by f of x and the x-axis from a to b with constant density rho. Okay, so rho is just going to be a constant. That means that our material, we're going to assume, is the same density all the way across. So, here's our function. And let's just say that our y-axis is over here. So this is our x-axis and this is our y-axis, and we're going from a to b. And this is our function y equals f of x. So here's the trick. The trick is to do what we always do, which is to partition a to b. Okay, so partition AB into n subintervals, right? So this is going to be x sub 0, and the next one's going to be x sub 1, and of course these all have with delta x. x2, this keeps going and going and going. This is xn. And so here's the trick, or the idea. The idea is that we're actually going to chop this up into a bunch of rectangles. And yeah, sorry, those don't look very straight. Let me try to get a little better here. And so we do this all the way across. Let me go ahead and do everything with the following case. So here is my xi minus 1, and this is going to be my xi. And so let's look at this rectangle right here. Now, of course, we always have the idea of what height of this rectangle are we going to use. So I will tell you in advance, let's go ahead and call this entire rectangle here. So this rectangle that we are looking at, this is rectangle, we're going to call this guy Ri. Okay? So the idea is that if we can find the center of mass of this rectangle, we can actually find the center of mass of every rectangle and then treat them like n dots. So in other words, the strategy is to reduce the n rectangles to n particles by finding the center of mass of each rectangle. Okay, so this is going to be our strategy. So what we're going to do is focus our attention now on one rectangle. Let's just say that we're zooming in and this is our rectangle. Our rectangle looks like this. And remember, this is xi minus 1 and this is xi. And, our curve might look something like this. It's hanging out, going along. Now you'll notice something is I specifically chose the height of this rectangle to be above the midpoint. So the middle is right there. So the midpoint, remember this guy is xi bar. We call that bar same as we did in the midpoint rule when we were doing our approximations. So question here for this rectangle. What is the center of mass of a rectangle? Well, to help us find the center of mass of a rectangle, it helps to know the following symmetry principle, which, by the way, we are going to use all the time. So what is the symmetry principle that I'm talking about? So the symmetry principle says that if a region R is symmetric about a line L, then its centroid lies on L. So the trick is to realize that in any rectangle, the rectangle is always symmetric with a dotted line that cuts it in half, which means that the center of mass must lie on that line. However, the center of mass also lies on this line, right? Because the rectangle is symmetric with respect to both of those lines. So what that means is that our center of mass must be this dot right in the middle here. Okay? So what are the coordinates of that point? Well, what point would that be? Here's our x-axis, right? This is our x-axis. So this point has coordinate. First off, we are at xi bar, right? That's the x coordinate of that. And what would its height be? Well, the height of that is going to be half of the total height of the rectangle, which is f of xi bar divided by 2. So that would be that point. Okay, so that's the center of mass. In other words, we can pretend like that entire rectangle is basically just that dot that I just wrote down. Okay, so now what would the mass be? Okay, well, in general, guys, mass is always equal to density times area. Right? Because mass is, by definition, density is by definition mass per unit area. So what would the area of such a rectangle be? Well, that's easy, right? The area of this rectangle, so let's call this the area of rectangle I, is just going to equal base times height. Well, what's the base? The base is delta x. So we have delta x times f of xi bar. Let me write it this way. F of xi bar times delta x. Okay. So what would the mass be? The mass would be rho times f of xi bar times delta x. So here's what's going to happen, right? We've got these n rectangles, and each of them, essentially, we can pretend sits at that dot and has this mass. Okay? So now, what we can do is we can figure out what the total moment is with respect to the x-axis, and also the moment with respect to the y-axis. Okay? So let's go ahead and talk about its moment with respect to the y-axis. So the moment with respect to the y-axis of that, sorry, I wrote x, I meant y. The moment with respect to the y-axis for that ith rectangle is just going to be its x coordinate times the mass. So what is the x coordinate? Its x coordinate, as we see up here, is x I bar. So I'm going to write xi bar times the mass, which is rho f of xi bar delta x. Okay, so this is my. But of course, what we need to do now is add these all up, because that's just the moment with respect to y of the ith rectangle. So this implies that the moment with respect to y of the whole system, so let me write it this way, of R entirely, is just going to be the sum of all of these. And let me write it this way, guys. I'm going to write it this way, rho xi bar f of xi bar delta x. Now, of course, this is actually an approximate, right? Because if you want to be exact, you take the limit. So what happens when you take the limit as the number of partitions goes to infinity of this? You get the definite integral. And so this is what we get for my. For my, we actually get that it's equal to the integral from a to b of rho x f of x dx. Okay, so all I did was I took this guy and I wrote it as an integral instead. That would be the moment with respect to y. Now, what would be the moment with respect to x of the whole system? Well, by a similar process, we're just going to use this guy instead, right? We're going to use this guy instead. Okay, so let's go on to the next page here. The moment with respect to x of the ith rectangle is going to be, we're going to take the location, 1/2 f of xi bar, and we're going to multiply it by the same mass as before. It's going to be rho f of xi bar delta x, which becomes rho over 2 times, you'll notice we are squaring the function. So this implies that the moment with respect to x is approximately equal to the sum of all of these. Oh, I forgot the delta x over here. So it's going to be rho over 2 f of xi bar squared and then delta x, which means that the real answer is if you take the limit as n goes to infinity of this partition, you get an integral. So you get the integral from a to b of rho over 2 times f of xi bar squared. Sorry, this would be f of x. Let me back up a bit. Dx. So we've got our mx. Our mx is right here. And we had our my, which was on the previous page, right? In the previous page, we had our my, which is right here. We have one more piece of the puzzle, which is the mass. What is the mass? Well, the mass, as we know, the mass is equal to density times area, right? Density times area. But we already know what the area under a curve is. Isn't this just a definite integral from Math 60? So in fact, we end up with the following. Rho times the integral from a to b of f of x dx. Because the area under a curve is always that definite integral, right? We just integrate the function. So finally, we're ready to write down the formula. This implies that x bar, remember, is my over m, which is going to equal, my was the guy on the other page, so my is this guy that I boxed over here, so it's going to be that integral divided by the other integral, so it looks like this. This integral divided by this integral. Now, here's the thing about this. I sometimes heard students say, can't you just cancel these two integrals or the f's in there? That's not how integrals work. However, we can cancel something, which is that rho, because the rho is just a constant. In other words, it pulls out of both and we can just cancel it out. So if we cancel that out, we actually get the following. By the way, this bottom guy is really just the area under the curve. So if we call that a, we get the following. 1 over a times the integral from a to b x f of x dx. So this is x bar right here. And what would y bar be? You do the exact same thing except with mx over m. So this is equal to, now we have the integral from a to b of, remember we have a rho over 2. And then we have this guy right here, which is the function squared. And then dx divided by the mass, which would be the rho times f of x dx. But again, guys, the rho's cancel. And again, this you can call a. Notice we have the 1/2 that can pull out as well. So an easier way to remember the formula is you pull out the 1 over 2a. And we end up with the integral from a to b of f of x squared dx. Okay, so together these two guys give you the centroid. This is x bar and this guy is y bar. Let me clean this formula up just slightly here because that looks not very good. Okay, so these are the formulas that we need to remember, and don't forget that the a, of course, is equal to the integral from a to b of f of x dx, okay? So for every center of mass problem, you do have to solve 3 integrals, although we are going to see that sometimes you can use symmetry to help you with these problems. Okay, now, before I do some examples showing this, there are 2 other things I need to talk about. What if your region, your lamina, is bounded above and below by 2 different functions? So let me write this out here. What happens if, so suppose R is bounded above by f of x and below by g of x. So let's say your shape looks like this. And this is f of x and this is g of x. Well, all you have to do is use subtraction, okay? So the center of mass of a shape like this is just going to be the center of mass of one minus the center of mass of the other. And so you end up with the following, okay? In this case, my would be the integral from a to b of rho x f of x dx, this is the moment of the top, minus the integral from a to b of rho x g of x dx, which we can combine into a single integral. But we need to be careful here. You can pull out the rho and the x, those factor out. But what's left is f of x minus g of x, right? So this is your moment with respect to y. What would the moment with respect to x be? This is going to be, you just subtract both of them. So this would be rho over 2 times f of x squared dx minus the integral from a to b of rho over 2 times g of x squared dx. Now you have to be careful because even though you could factor out the rho over the 2, you're still going to have a function squared minus the other function squared. So this is what it looks like. The integral from a to b of rho over 2, and then what's left is one function squared minus the other function squared dx. Now be careful, this does not equal, so do not do this, okay? This is a common mistake that I see. This is totally wrong. Do not do this, okay? F of x minus g of x quantity squared is not the same thing as squaring both of them first. You're going to square them both first and then subtract them, okay? And then, of course, you do the same thing, right? You still divide these by m. What would m be? Oh, let me go back to my last color. So m, you guys have already found the area between two curves like this before in Math 60 in single variable calculus, part 1. So we know that this is equal to rho times the top function minus the bottom function, dx. And then finally, you know that x bar is equal to my over m, and y bar is equal to mx over m. Okay? So I'm going to do a couple of examples here using these formulas, and so that we can practice finding the center of mass. There is one thing I will write down before we do some examples. As a hint here, this is super important. As a hint, a time saver here. Maybe hint is the wrong word. Let's go with tip, okay? Because this is really a tip here. Tip. Use the symmetry principle whenever possible. Sometimes using the symmetry principle can help you solve a problem very quickly because you will get for free that the center of mass lies on a particular line, and that can actually eliminate one of the integrals you have to do. So use it whenever possible. And another thing I should say, maybe I'll call this tip number 2 on the next page. So tip 2. Try, and this is something I always encourage, try to approximate the centroid before solving the problem. This helps us find out if our answer is reasonable. Okay, so let's go ahead and do an example. This is number 2. Find the centroid of a semicircular plate with constant, not radius, I meant to write constant density rho, and radius 1. So we're going to draw a picture of this thing, and it really helps to immediately draw a coordinate system, and I'm going to go ahead and draw the coordinate system this way. In other words, this is 1, and that's -1, and this therefore is 1. Okay, so this is our semicircular plate. We've got a coordinate system there, and before I do anything, I want to approximate the centroid before we start. Where is the centroid going to be? I like to pinpoint where it's going to be beyond the halfway points of the x and y coordinate. Let's think first if there's any symmetry here. And I do notice symmetry. Don't you guys notice that this graph, I mean, I even drew it as the picture like this on purpose. Notice that it is symmetric with respect to the y-axis. This implies that the center of mass lies on that y-axis, right? So that means that x bar is equal to 0. Which is really cool. We've saved one whole integral that we don't have to do, which out of 3, that's not bad, okay? And what about y bar? I can't tell you what y bar is exactly, but I can say something. I know that y bar is going to be below this dash right here. So this would be at a half. How do I know it's below? Because there's more area below that, right? So that means it's got to be pulling the center of mass down. So if I were to pinpoint where the center of mass would be, I would guess somewhere like right over, maybe like right there. Okay. In other words, this is how I write my approximations. I say that y bar has to be between 0 and a half. Okay, I'm doing that so that later I can check to see if my answer makes sense. So how do I find y bar? I've actually got to solve a couple of integrals here. First off, remember I need the area of the shape we're talking about. So the area is equal to, I know I'm going to integrate from -1 to 1, but I also already know what the area of a half circle is, don't I? The area of a half circle is going to be pi times r squared. In this case, r is 1, but then divided by 2, so that's pi over 2. Okay, so this is nice. I'm going to save that. Now let's go with y bar. If we look at our formulas on the previous page, if I scroll back here, x bar is equal to, let me go one more here. X bar is equal to, it's 1 over 2a is going to be y bar, integral from a to b of the function squared dx. So let's come back here. Let me write the formula down. It's 1 over 2a times the integral from a to b of what? It's going to be the function squared. Let's write it this way. F of x squared dx. So what's this going to equal? Well, I already have the area on the left here, so I'm going to take this guy and I'm going to plug it in for a right here. And so that gives me 1 over 2 times pi over 2 is just 1 over pi. I end up with 1 over pi, and then I'm going to integrate from -1 to 1, and I'm going to square the function. Well, I still actually haven't told you guys what the function is, but isn't the function of a semicircle the square root of 1 minus x squared? So that's a semicircle, except I'm going to square it, which you can already see is nice because the square is going to make the radical go away. And so we end up with 1 over pi times the integral from -1 to 1 of just 1 minus x squared dx. Now notice too that this is an even function, so I can use a trick of symmetry from calculus 1. Instead of going from -1 to 1, I can double it and go from 0 to 1 of 1 minus x squared dx. So what would that antiderivative be? This is going to equal 2 over pi times x minus 1/3 x cubed, and I'm going from 0 to 1. If I plug in 1, I get 2 over pi times 1 minus 1/3. What does that equal? That's 2 over pi times 2/3, which is equal to 4 over 3 pi. Now, what would that be on a calculator? 4 divided by 3 pi is approximately 0.42. So look guys, this actually matches what we said over here, right? Look back over here. I said that I knew the answer was going to be between 0 and a half, and it was. It was actually 0.42. Anyway, we've got our answer then. Our center of mass, our centroid, is going to equal 0,4 over 3 pi. So this is the center of mass of the shape. Okay, let's go with example 3 now. Again, we're going to find, this time let's get some functions. Find the centroid of the region bounded by the curves y equals square root of x, y equals 0, and x equals 4. Let me make that a little more clear. So what does this curve look like? Y equals square root of x, y equals 0, and x equals 4. Well, if we see where y equals square root of x and x equals 4 meet, these two meet at the point 4, 2. And so if we were to draw a picture of this, it looks something like this. So if that's 4, maybe that's 2. Oh, that's no good. Let me try that again. Something like that. And so we are looking for the center of mass of this. Now notice that there is no symmetry here, so we are not going to be able to use the symmetric principle or the symmetry principle. Okay, but we still can take a guess as to where this would be, right? We know that if this is 2, the halfway point would be 1. We could see that there is more area below the halfway point than above, which means we know from this that y bar is between 0 and 1. Furthermore, if we look at this picture, if that's 4 and that's 2, we could see that there's more area to the right. So if I were to guess where the center of mass would be, well, this tells us that x bar is between 2 and 4. So the center of mass in my mind is somewhere over here. Let's see where it is after we're done with this problem. Okay, so let's start with the area. usually start with the area here. The area is going to equal the integral from 0 to 4, 0 to 4, of the function, which is the square root of x dx. This should be a really easy integral to do. So this is going to be 2/3 x to the 3/2, and we're going from 0 to 4. And this is going to equal 2/3 times 4 to the 3/2 minus 0. What's 4 to the 3/2? The square root of 4 is 2. 2 cubed is 8. So we end up with 16/3. So this is the area. We're going to use that later. Let's do x bar now. X bar is equal to 1 over the area times the integral of x times f of x dx. And we are integrating again from 0 to 4. Now the f of x, in this case f of x, remember, is the square root of x. So if this is the square root of x, that's x to the 1/2. If we multiply it by x, we get x to the 3/2. And so we're going to have the following. 1 over the area, so that's 3 over 16, right, the reciprocal. Integral from 0 to 4 of x to the 3/2 dx. So what is this equal to? We still have 3 over 16 times, if we add 1 to the exponent, that's 5/2, but then reciprocal is 2/5, so it's going to be that times x to the 5/2, and we're going from 0 to 4. So what is this going to equal? I'm going to reduce here. So this is going to be 3 over 40. Sorry, let me make that a little more clear. 3 over 40 times 4 to the 5/2. 4 to the 5/2 is 2 to the 5th is 32. So this is equal to 3 over 40 times 32. If you take out an 8, that's 4 over 5. So you end up with 12 over 5. 12 over 5 for x bar, which, by the way, what is that? That's 2 2/5, so that's 2.4. And that's x bar. Does that answer make sense? Yes, it does, because I want you guys to look over here. We said that it was going to live between 2 and 4, so that makes sense, 2.4. Next, how about y bar? Y bar, remember that formula is 1 over 2a times the integral from 0 to 4. This time we're going to take the function, which is x to the 1/2, and we're going to square it. So twice the area is 32/3, but we're going to do the reciprocal, so that's 3 over 32. Okay, 3 over 32. And we're going to integrate from 0 to 4, and we just have an x there after squaring it. So what is this equal to? This is 3 over 32 times 1/2 x squared, going from 0 to 4. But if we plug in a 4 there, we get 16. So this is equal to 3 over 64 times 16, 1, 4. We get 3/4. Look here, guys, this is 3/4, and we noticed we said that it was going to be between 0 and 1 over here. So this is very good. This was a good approximation that we made, and so we're ready to write the answer then. The centroid is equal to, well, let's see, x bar was 12/5, so I'll write it as a fraction, why not? And then 3/4. Okay, let's do another problem. Actually, before we do this next problem, I want to give you guys one more kind of, not an extra set of formulas, but I actually want to show you guys what happens if we are dealing with functions of y instead of functions of x. So suppose we have the following scenario. Let's suppose that x is equal to g of y, and y goes from c to d. And we want the center of mass of that. So everything we did before, the formulas stay the same, except x and y switch roles. This actually means that the x formula becomes the y formula and the y formula becomes the x formula. So what does this mean? So this means that x bar actually becomes the 1 over 2a formula, and then the integral from c to d of y times g of y dy. And, oh, sorry, I did that wrong. This should be g of y squared. Let me fix that. And y bar is going to equal 1 over a times the integral from c to d of y g of y dy. Okay, so it's easy to make this mistake, but just remember that when you have x equals g of y instead of y equals f of x, you do have to switch the role of x and y in the formulas. What that means is that the formulas actually switch places. So let's go ahead and do another example. I'm going to also find the centroid of a region bounded between some curves. So this is going to be number 4. Find the centroid of the region bounded by the curves y equals x cubed, x plus y equals 2, and y equals 0. Now this is a more complicated one because we have 3 different functions, and so we actually need to figure out where these functions meet. Okay, what this shape looks like. So what does y equals x cubed look like? So y equals x cubed looks something like that. Next, x plus y equals 2. This guy becomes y equals negative x plus 2. So if we were to go up 2 spaces here, this has a slope of negative 1. So we actually know that this is going to pass through this point, right? This point. There's our straight line. Sorry, it doesn't look very straight. Finally, y equals 0 is the y-axis, and so the region that we are talking about is inside of here, right? This is the region that we're talking about. Okay, so we actually have an upper function, which is y equals negative x plus 2. Let me get rid of this a little bit. So this would be y equals negative x plus 2. The bottom would be y equals x cubed. and we're going from 0 to 1. Now, if you had trouble drawing those, you could have always set the two equal to each other, and you would have ended up getting that same point here. Okay, this time what we're going to do is set up the integrals just to save time here. Let's go ahead and set them up. So what would the setups be? So first, the area. We know that the area between two curves is top minus bottom, so the area is going to be from 0 to 1 of the top function minus the bottom function. Now, this is not a difficult integral to do, but I will leave it fully set up, which means I will square it out, or not square it out, sorry, but I'll go ahead and get rid of that minus sign in the middle, and I'm going to write it in descending order. It becomes negative x cubed minus x plus 2. So this becomes our area. Let's go ahead and write that down. This is the area. And then let's go ahead and write x bar. X bar is 1 over the area times. Now, we got to be careful here because we are going to do a subtraction here. Because remember, it is, it's going to be the integral of x times f of x minus g of x. Right? We have to subtract the two functions. So this means that x bar is equal to 1 over the area times the integral from 0 to 1 of x times the top function minus the bottom function. And from here you would distribute the x and all that stuff, but we're not going to do that. We're just going to box this. And how about y bar? Y bar is going to be 1 over 2a. And we're going to integrate, and this time we're going to do the first function squared minus the second function squared dx. So this is going to be 1 over 2a times the integral from 0 to 1. The top function squared is negative x plus 2 squared minus, and then we have x cubed squared dx. And you would work through all of that algebra. Okay, guys, and that concludes this section. Thank you for watching.